Deep beneath the surface of the North Sea in 1945, the crew of the Nazi U-1206 was hiding from Allied planes. They were sealed inside a steel tube, shuddering under the massive weight of the ocean above them. In a combat scenario like this, the margin for error drops precisely to zero. The captain needed to use the toilet, but he turned the wrong valve. In seconds, highly pressurized seawater blasted backward through the plumbing. It fled the compartment and poured directly into the vessel's battery bank, triggering a chemical reaction that immediately began filling the air with lethal chlorine gas. Choking on toxic fumes, the crew had no choice but to blow the ballast tanks. The moment the U-1206 breached the surface to vent the gas, waiting British forces spotted the vessel, destroyed it, and captured the surviving crew. To understand how easily a mistake like that happens, you have to understand the physical reality of living in a submarine. A standard prison cell gives an inmate about 80 square feet of room. Down here, a sailor gets roughly 20. Your personal space ends exactly at your shoulders. A submarine is a deeply unnatural environment. It is a sealed, artificial world entirely surrounded by instant death, where flawless engineering and absolute procedural discipline are the only things keeping the ocean out. Before you even worry about external water pressure, you have to deal with the immediate biological reality of 130 men breathing inside a sealed can. Every inhalation drains a finite supply of oxygen, and every exhalation pumps out toxic carbon dioxide. This animated schematic breaks down how they solve the oxygen problem. Submarines pull in the surrounding saltwater and use an electrical current, a process called electrolysis, to force the molecules apart. The system rips them apart, piping the fresh oxygen directly into the cabin air while venting the highly volatile hydrogen gas out of the ship. But generating oxygen is only half the battle. The diagram now shifts to the scrubbing system. Cabin air is forced up through a vertical tower, passing through a chemical liquid amine spray. This mist acts like a chemical sponge, absorbing the carbon dioxide before it can reach a fatal 10% concentration in the air. If the mechanical scrubbers fail, crews rely on backup canisters packed with a chemical called soda lime, which turns the CO2 gas into a solid carbonate. But there is a massive logistical flaw. Once a canister is full, it becomes a piece of heavy, useless trash, taking up precious room in an already cramped ship. Survival relies entirely on this relentless chemical balancing act. If the machinery stops making oxygen or stops destroying carbon dioxide, the crew suffocates in minutes. Air isn't the only thing they have to manufacture. The ocean outside is completely undrinkable. So, modern submarines force the surrounding saltwater through high-tech reverse osmosis filters, or boil it into steam using nuclear reactor heat, synthesizing fresh water drop by drop. Because this water generation takes immense energy, rationing is extreme. A sailor doesn't get a 15-minute morning routine. Showers are strictly timed and limited to exactly 60 seconds of running water. Food is another severe bottleneck. Look at this cutaway illustration of a submarine corridor. To keep 130 men fed for 200 straight days, a vessel loads roughly 20,000 kilograms of food. Since there is no dedicated cargo hold, the crew actually walks directly on top of their supplies. If you look under their boots, the floorboards are entirely lined with dense layers of canned and frozen goods, and the crew eats constantly. The immense physical strain and psychological tension of operating underwater causes the body to burn calories at an accelerated rate. To combat extreme fatigue, especially for the night shift, the kitchen serves a mandatory fourth meal at midnight, universally known as midrats. Every single calorie and every drop of water is meticulously tracked. The human body is treated identically to the vessel's engine, a high-performance machine requiring precise, constant, and calculated refueling to prevent sudden failure. This cross-section of a submarine hull illustrates exactly why the U-1206 sank. Flushing waste out into the ocean means opening a hole in the hull. The internal sanitary tank sits right on the boundary line between the safe, low-pressure cabin and the massive external weight of the deep ocean. Getting rid of that waste requires opening internal and external valves in a highly specific sequence. Notice what happens if the outer valve opens a fraction of a second before the internal tank is fully pressurized. The entire weight of the ocean is flushed backward into the submarine. Navigating that kind of pressure requires absolute focus, which brings us to the severe physical exhaustion the crew faces. This photograph shows men cramped against heavy machinery, illustrating the complete lack of a quiet, private place to recover. There physically isn't enough room for everyone to sleep at once. A vessel might carry 135 sailors, but only have 94 beds. The solution is a system called hot bunking. The moment you wake up for your shift, another sailor whose shift just ended crawls directly into your spot. The bed is still warm. Normal human recovery is entirely erased. Sleep is mathematically engineered into artificial cycles, ensuring the vessel's machinery never stops running and the human cogs never stop turning. You can engineer the oxygen, distill the water, and manage the pressure, but there is one variable you cannot engineer: the human mind. After months trapped in a windowless tube with the same smells, the same faces, and absolute isolation from the surface, the psychological toll is severe. Without natural sunlight, the brain's circadian rhythm collapses, leading to deep depression and anxiety. To counter this, submarines use sensory hacks, bathing the corridors in bright white light to simulate daytime, and switching entirely to red light to signal to the crew's brains that night has arrived. But even with these hacks, the mental fatigue is a deadly threat. A tired brain makes mistakes, and in an environment entirely unforgiving of error, a single miscalculation is fatal. In October 1944, the crew of the USS Tang experienced this firsthand. This tactical schematic tracks what happened. The Tang fired a torpedo, but a mechanical failure caused the weapon's steering mechanism to jam. Instead of flying straight, the torpedo locked into a circular trajectory, looping entirely backward and detonating directly into the submarine. Submariners operate in an environment where routine bodily functions require tactical precision, and a single bad valve sinks a warship. Their daily fight is against the crushing weight of the ocean, the unforgiving complexity of their own machines, and the absolute limits of the human mind.